Hi, NA Physics. It's Mr. Neff here. Today, let's talk about work. Now, work is the first of two units that we're going to talk about conservation laws. And when I say conservation laws, I say how do things really stay the same? How does a quantity like energy and later momentum really stay the same? Even though it might, to the first glance, it might look like it's changing. And also, what we're looking at here is the effect of a force. Now, we know that a force has the effect of accelerating an object or potentially accelerating an object if it's not canceled out by another force. But then, what about the duration? What about over how many meters does the force act? That's the focus of this unit. What about over how many seconds does the force act? Well, that's the focus of the next unit. Now, these questions were really tackled by two scientists, among others. And I have a scientist on the left who tackled the idea of a force and a displacement over which it caused, over which it acted. What's that about? Well, you're going to find that when you're talking about force and distance, force, displacement, newtons, and meters, you're talking work, you're talking energy. Later on, we're going to talk about the contribution of the other scientist, and we've already seen this scientist before. This is going to be the contribution of a force and a time. Over how many seconds does it act? What's the effect of all of that? You're also going to see that the talk about forces, displacements, work, and energy, that's going to be very focused on scalars. I'm not going to say everything is going to be a scalar, but a lot more scalar type talks for us. In contrast, the force and time, even though that time is definitely a scalar, this is going to be a lot more of a vector talk. And the reason is because we're going to take that force, which is a vector, and multiply it by a time, which is a scalar, and we're going to retain the vector. Versus, if we take the force, and one way to multiply, quote unquote, multiply forces together is to do this thing called a dot product. And a dot product is going to say to take the components of the two that are parallel to each other and multiply those, and just think of it as a scalar at the end. And so even though the displacement and the force are both vectors, the result is going to be a scalar. Now, who are these individuals that made these contributions? Well, by now you've been guessing in your mind who are these guys, and certainly the guy that's on the left is James Joule, and certainly the guy that's on the right, who we have been talking about, is Isaac Newton. Our work talk is really going to be about changes in this stuff called mechanical energy. And this isn't the first time you've talked about mechanical energy with a teacher. They cover this usually in elementary school, they cover it again in middle school, and so this isn't the first time, but we're going to go into it a little bit more mathematically and maybe a little deeper than maybe you did before. Now, when I say mechanical energy, I'm talking about energy that can be seen and that it's able to do work directly. I'm going to say there are three forms of mechanical energy, One form being sort of the highest form, and then the other two forms will be sort of secondary forms that will also contribute here. And then you'll be able to think of lots of other kinds of energies too. You'll see I have them at the bottom of the slide. And they're going to be more like third-class forms of energy that need to be converted first. So the energy that something has because it's moving, we call it kinetic energy. You've heard of that before. Why did I pick the cheetah? Well, I picked the cheetah as an example of that because number one, it's very fast, but number two, it's not that small of an animal. And so if you saw this cheetah running, if you saw that this thing had some velocity, you certainly wouldn't get in front of it. You'd know just by looking that it was dangerous. You might say, yeah, cheetahs are dangerous because of the teeth and the claws. That's another reason why they're dangerous. But they're dangerous because they're fast-moving objects, fast-moving pieces of mass. And so aside from the teeth, aside from the claws, if one ran into you, you'd be in bad shape because it has this stuff, this kinetic energy. We're going to abbreviate that with Ke. And so that means it's able to do work on you. What do I mean exactly by do work on you? Well, you could think of it as injuring you. You could think of it as having a reason to be afraid of it, but we'll talk about that more as time goes on here. Now, I also picked another picture here. I picked a picture of a boulder, piece of petrified wood, it looks like in this picture, that's ready to fall off of a cliff. You can see that's dangerous too. Something that has the ability to fall down has what we call this gravitational potential energy. In middle and elementary school, you just called that potential energy, but I've got another form, so I have to specify that this is gravitational potential energy. You can see a mile away that this is dangerous, because if you were over here, you'd know that you were in danger. That this thing, because it has mass and because there's an ability for it to fall, that is, it could fall a height, well, it has a gravitational potential energy. The other reason is there's something constantly pulling down on it, and that's it has an acceleration from gravity. And so this mass, this little g, and this height are going to be factors that are going to contribute to how much gravitational potential energy that has. By the way, we usually put in a symbol for potential energy as a cursive capital U for potential energy. And you're going to see me do that too. Now, because I have different kinds, I'm going to put a subscript G on this, not to mean little g like the acceleration from gravity, but still gravity. And so gravitational potential energy will be that symbol, where again, kinetic energy will be this Ke. Now, the last picture that I have here is a picture of a garage door spring. Now, a garage door spring, a lot of you are going to have a spring just like this at your house. Some of you may be one that's sort of like this, but it twists and it's over top of the door rather than being parallel to the track that the door runs on. But regardless, garage doors for the most part are really heavy, and so a person or a garage door opener is going to need some help from some energy to get that thing lifted up there. So what it has been engineered here is they've attached some springs which either can twist or they can stretch like this one, and they can store some energy. And so when you see that spring is stretched out, that is, the coils are farther apart than they would have been when it's in a relaxed state. You can see that that thing is holding energy. You can see that that thing is dangerous. And so you wouldn't get on a ladder and start messing around with that. You'd know that that was something that a professional should be doing. And if one of your parents saw you messing around with that, they would say, "Hey, what are you doing? Get out of there. That's can't you see that that's dangerous?" Well, sure, I see that it's dangerous. This is a kind of potential energy too, and we say that it's elastic or spring potential energy. Occasionally, you'll see someone call this UE for elastic potential energy. I'm actually going to avoid that because we're coming to an electrical potential energy in the future, and so I want to use that symbol for electric potential energy. So I'm not going to X it out like it's wrong, but I'm just going to say that the one I'm going to use is a USP for spring potential energy. So that's a little bit more the one that we're going to use here. You can see that the point that I'm making is all of these are similar to each other in that you can readily see if the energy is there or not. You can tell that the cheat is moving. You can see that the boulder could fall. You can see that the spring could spring back to its original shape. And so no one's going to be surprised whenever these things hurt them, right? You can tell a mile away that they're dangerous. Now that's different for some other kinds of energy. Thermal energies, internal energies, chemical potential energy, electric potential energy. You can't really see those things well. Look at that water. Is it dangerous? I don't know. Basically, I'm asking, what's the temperature of it? Is it hot that you could burn yourself on it? Is it cold that you could get frostbite from it? I can't tell by looking. It could be completely safe. It could be very dangerous. Is there energy there? Sure there is. But I'm going to say there's more of a third-class kind of energy that you'd have to convert to one of the mechanical forms before you could actually get it to do work for you. Chemical potential energy, those things are things like food and gasoline. They're great. We spend a lot of money on them. But if you don't have a way to convert these, like by eating the food or by having an engine that could convert the chemical potential energy into gasoline to another form, well, then they're of no use to you, right? No one buys gasoline who doesn't have an engine for it. No one buys food who's not going to eat it, right? And then electric potential energy. We have these batteries. Are these batteries, is there energy inside of them? I can't tell. I'd have to put a meter on them, or I'd have to put them in something and see if they actually work. I can't tell just by looking. So see, are these valuable forms of energy down here? Of course, but you can't tell by looking. And that's why they're not mechanical. Mechanical forms of energy, you'll be able to tell by looking. If it's there, if it's energized, if it's not. If it's capable of doing something, or if it's not. but the other forms of energy you won't be able to tell. Now, prior to the 1840s, and I know we're going back a ways, it was thought that mechanical energy, those things that I just talked about, and internal energy, that's like that energy in the gasoline, or that's the energy of the temperature, because of the temperature in that beaker of water. Well, those things they were thought to be very, very different, that the mechanical energy was very different from this internal energy. Well, James Joule is a well-known name now because of his demonstration that showed that those two things actually aren't that different. See, and I don't want to go into great depth here, but one thing that James Joule did is he showed that a falling mass, which is going to lose gravitational potential energy and turn gravitational potential energy into kinetic energy, right? A little bit here, this thing will be moving down, and it will be falling, and it'll have kinetic energy. But the other thing that it can do is it's going to do work on this string. Now, I keep using this vague word work. What is that exactly? But I'm not using it that different from what you have. I'm saying it's an ability to accelerate something. It's an ability to change the state of motion of something. All that to say, this thing is able to do work on the string, which then is able to do work on the shaft, and that's able to turn these propellers. Now, if you know anything about the experiment, Joule had the propellers spinning some water, which he showed that the temperature went from a lower temperature to a higher temperature. So the temperature went from that to that as this spinning happened. And so he's in essence showing that gravitational potential energy and then later kinetic energy are being turned into internal energy. And so that if you were converting from one to another, how different could they really be? That idea is what makes Joule a household name today. So I keep saying the word work, 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 work. What do I mean exactly when I say work? Well, I can't define it for you as maybe as satisfying as a way that you'd like, but I'm going to do my best. So when we say work, we mean an amount of energy transferred to an object because a force causes a displacement. Now there's a lot there, a really lot there. We're going to transfer some energy into or out of an object because a force is causing a displacement. So as I led in with at the beginning of this video, we see the effect of a force. A force and a displacement, I'll use delta x for that like I did in kinematics. We see those two things together are going to go into the work. And actually it turns out that all you really need to do is take the amount of both of them that are in the same direction. We call that that idea a dot product. Not that we're going to dwell on that too much, but we say that if we take the amount of the two of them that are in the same direction and we multiply them, then we can get this work. So it's the effect of a force because of how far it pushed. Now you know work when you see it because an object is made more capable or less capable of doing work on its own. So that is, you're making an object more or less dangerous or more or less able to do something, to push another object. Now, work is easy to understand if you could just understand what energy was. So if you look up the word energy, you will see that it's defined as an ability to do work. That's very disappointing, am I right? Ability to do work. I wanted to understand work, so I looked up energy, and now I'm looking up work to understand energy. So it's a circular kind of logic. Why is this like this? Well, we as humans have only been studying this for a couple hundred years. Remember I said 1840, we're not even at 2040 yet. And so all that to say, when we were in mechanics for 200 years, we were still on earth, wind, fire, and water, and natural and violent motion with Aristotle's physics. We still thought that the sun was the center of the universe, the earth was the center of the universe, and we really weren't very advanced yet. So we haven't been doing this for very long. That ought to excite you. Maybe you're someone who can make a contribution to the world in terms of these ideas of work. Now, next time we will talk about how you actually calculate the work. How do you really know it when you see it, and how do you do that calculation? We'll see you next time.